Swayam Prabha. Digital India. Educated India.
Welcome to the 16th lecture in our particle characterization course. In the last lecture, we started discussing adhesive phenomena between particles and surfaces and also between adjacent particles. In particular, we dealt with the case of van der Waals forces of intermolecular or interparticulate adhesion, which are predominant in the case where the adhesion is happening in gaseous medium. We noted that the van der Waals forces are very much dependent on the Hammaker constant, and we established a relationship between the Hammaker constant for a system and the associated van der Waals force of adhesion. And the key point there was that the geometry of the particle plays a significant role in determining not only the magnitude of the adhesion force, but also the qualitative dependence on properties such as the size of the object as well as the distance between the objects. And we also noted that the intervening medium plays a significant role in either enhancing or reducing the force of attraction. And finally, we discussed aspects such as the hardness of the surface and the roughness of the surface and their influence on the van der Waals force of adhesion. Now, in today's lecture, we are going to take up the topic of electrostatic attraction between a particle and another particle or a surface. Electrostatic forces are quite strong, particularly again in air or gases or vacuum as the medium. Electrostatic forces are typically weakened when you take the particle system or a particle surface system and immerse it in a liquid such as water. There is an immediate order of magnitude reduction in the forces of electrostatics between these surfaces, but certainly again in dry environments it plays a considerable role. Now, we are all familiar with some forces of electrostatic attraction, the Coulombic forces. I am sure you have all dealt with in your earlier courses. The Coulombic force is basically reflected as follows. So, if you have a particle and a surface, and this particle diameter is some dp, and this distance is again some z0, and let us say that this particle is carrying a charge q. So, it is a charged particle, and let us say that the surface is also charged either with the same charge or an opposite charge of q. The associated Coulombic force can be written as q squared over 4 pi epsilon 0 epsilon r times z0 plus dp by 2 the whole squared, which is the distance between the center of the particle and the surface. Here epsilon 0 is the permittivity of free space, and epsilon r is the dielectric constant of the medium. So, we know how charged surfaces or charged particles interact and the force that develops between them, but if you have a charged particle and let us say you have a neutral surface, is it still possible to develop a Coulombic force of either attraction or repulsion between them? So, in that case you again have a particle of diameter dp, charge q, and you have a surface with a distance of separation of z0, but let us say that the only difference is the surface itself is neutral. It turns out that even in such a case a Coulombic force does develop between these surfaces. Essentially this particle is reflected as an image inside the surface at a distance that is also exactly equal to z0. It is like a mirror or an image that it sets up, and so in this case the force associated with that is called the image force, and this is given by q squared divided by 4 pi epsilon 0 epsilon r. The distance of separation now between the two bodies is roughly twice what it was in the previous case, right. So, we write this as dp plus 2 z0 the whole square. So, the image force is roughly equal to a quarter of the Coulombic force that prevails between two charged surfaces or two charged bodies. So, it is substantially weaker, but non-zero. So, even when you have a neutral surface and you have a charged particle approaching it, or when you have two particles in which one is charged and the other is not, you can still set up a Coulombic force between them. So, that is an important consideration that we need to be aware of. Now, the other type of electrical force that can be set up between two surfaces that are again in air or a gaseous medium or in vacuum is called the electronic double layer force. And this force is associated with the electrostatic contact potential between the two solid objects. In fact, the force is also known as the contact potential force. Now, how does the electrostatic contact potential happen? This potential is created because of differences in the energy states as well as essentially the electronic work functions of particles that are adjacent to each other. Now, there is an immediate tendency then for the particles or the two objects to equilibrate. This equilibration proceeds until we reach what is known as a constant Fermi level. Electrons are transferred from one object to another till this constant Fermi level is reached across the pair of objects. Now, as this process proceeds of exchange of electrons, you set up a potential between the two surfaces, and that is known as the contact potential. Now, this electrostatic contact potential can be quite significant. So, this potential Vcp can be of the order of half a volt. So, that is quite large. Particularly this force is especially important for finer particles. The force essentially increases somewhat linearly with respect to the inverse of the particle size. Although we will see that the potential itself is proportional to the particle size. However, as particles get larger, the tendency to equilibrate by exchanging electrons actually decreases. So, the linear dependence on particle size of this potential is only applicable in finer size ranges, not in the larger size ranges. Now, basically this potential sets up an electronic double layer between the two objects. Now, this double layer can actually extend even into the object. For example, especially if you have a dielectric particle, semiconducting particle, or an insulating particle, and you have two particles that are adjacent to each other, this field can actually extend into the particle up to 1 micron within the particle. This is for, again, insulators and semiconductors. However, for a conductor like a metal, the force stays only on the surface. In other words, the potential or the electronic double layer is restricted to the surface of the particle. It does not extend into the interior or bulk of the particle. So, this electrostatic contact potential is again an important force that can either attract or repel particle pairs or particle to surface pairs, and the force in this case F, contact potential, is proportional to the square of the voltage or the potential that is set up times dP, times there is also a pi and epsilon, and the distance plays a role, but the difference here is that here you have a z0 squared dependence, whereas in that case you have a z0 dependence. What that means is the contact potential force is an action at a distance. It can act over much longer distances compared to the Coulombic force. So, another way to imagine this is if you have two particles that are separated, then the contact potential force is dominant until they reach a much shorter distance of separation, at which time the Coulombic forces start to become dominant. And similarly, when we look at particle size, as the particle size increases, the Coulombic forces gain in magnitude. As the particle sizes decrease, the electrostatic contact potential forces become important. Now, this equation, by the way, is for a spherical particle and a highly polished surface. The equations can be quite different and much more complex when dealing with irregularly shaped objects, as well as again parameters such as rough surfaces or asperities on a surface and so on. But in the simplest case, we can represent the force associated with contact potential in this fashion. Again, the reason that this develops is because of an imbalance in the energy states of adjacent particles and the associated tendency to exchange electrons till they are neutralized. Now, in the case where the particle is actually immersed in a liquid, something analogous happens, except that now instead of an electron distribution, it is an ionic distribution that happens. So, in the case where the particle is immersed in a liquid, the potential that develops is called an ionic double layer potential, also known as zeta potential. Now, the zeta potential happens particularly in liquids of high ionic conductance. And that typically requires high concentration of electrolyte. So, when you prepare an electrolytic solution in which you have a large concentration of ions that are dissolved in the solution, what happens is a distribution of these ions. So, let us say that you have a situation where you have a surface and on top of that you have a liquid, and in the liquid you have particles. And let us say that in this liquid you have various ions, positive and negative ions that are floating around. What are these ions going to want to do? They want to attach themselves either to the particle or to the surface or both. Now, if it happens that, let us say that you get a bunch of negative ions attaching themselves to a particle because they are attracted to it, and if the surface also has a negative ion buildup, then there is going to be a repulsive force between them. Similarly, if you have a tendency for adjacent particles to accumulate charges of the same sign, again they will repel, whereas if they build up charges of opposite signs, they will attract. So, every particle has what is known as an ion cloud around it, which happens because particles have a natural ions have a natural tendency to separate themselves from the electrolytic solution and attach themselves to the nearest solid that they see, and this essentially can be visualized as a layer of charges that are built up around the particle. So, if you have one particle with a certain charge buildup and you have an adjacent particle with let us say the opposite charge, this again sets up a potential between them, which is known as the zeta potential, and that reflects in an attractive or repulsive force as the case may be. The definition of the zeta potential is the potential difference which is set up at the interface between the object and the liquid, where the definition of the object includes the ion cloud that is surrounding that object. So, the shear boundary that exists at the exterior of the surface charges is considered the interface, and so the potential is actually set up, if this is the liquid, the potential is set up between this boundary and the liquid that is surrounding the object. Now, zeta potential obviously has huge implications in manufacturing industries where you use slurries of particles in a solution. One of the examples is a polishing process that is used in semiconductor manufacturing called CMP, chemical mechanical planarization, which really makes use of abrasive particles that are in suspension to provide a high surface finish to wafer surfaces by the combined action of mechanical polishing as well as preferential chemical reactions with the material on the surface. Now, when you do this chemical mechanical planarization process, the size of the particle plays a huge role in its effectiveness. Now, what can happen again if you have high zeta potential in the system, depending on whether it's an attractive potential or a repulsive potential between the particles, you can either get a well segregated suspension of particles in solution, which is what you desire really. You require a high degree of dispersion of the particles, or if the particles carry opposite charges, you will start to see agglomeration effects. Now, as the particles change size from their original size ranges to the agglomerated size ranges, there is a resulting change in their polishing characteristics as well. So, that is one aspect. The other aspect is the zeta potential difference between the particle and the surface that you are trying to polish. So, here again, if you have a repulsive interaction between them, the nature of the polishing process is going to be very different compared to if you have an attractive process between the particle and the surface. So, in slurries, it is very important to characterize zeta potential. it has huge implications for the stability of the suspension. Again, if you can induce charges so that particles in suspension repel each other, they are likely to remain stable in suspensions much longer than if they carry no charge or if they carry an attractive charge. So, by essentially by controlling the zeta potential, which can be done for example by controlling the pH of the solution, by controlling the composition of the electrolyte and as well as the concentration of the electrolyte, you can influence charge buildup on discrete particles and cause them to either try to come together or move apart. So, many of the, for example, particle size analyzers that are used in manufacturing industries will also come with a zeta potential measuring device, because the simultaneous measurement of the size distribution and the zeta potential is important to characterize the long term stability of the suspension. So, if you measure a certain size distribution of particles at time 0, but your zeta potential measurements say that there is a high attractive force between the particles, then you can expect that over time you will see significant clumping of the particles and a significant size change. Whereas if the zeta potential is 0 or repulsive in nature, you can rest assured that even with the passage of time the particle size distribution is not going to change significantly because there is no agglomeration going on. Okay, let us say that you have set up this ion cloud and you have now set up a zeta potential. Again, there is a force associated with it, and that is called the ionic double layer force. So, the ionic double layer force is what prevails in a liquid, particularly in a liquid of high conductivity, and this force F IDL is given by 2 pi epsilon 0 epsilon r dp zeta potential of the particle, zeta potential of the surface times a parameter kappa times exponential of minus kappa times z0 over 1 plus exponential of minus kappa times z0, where again epsilon 0 is the permittivity of free space, epsilon r is the dielectric constant of the liquid. The zeta values are the zeta potentials that develop over the particle and over the surface, or it could be two adjacent particles. Kappa is the inverse of the double layer thickness. So, this parameter is very much influenced by the ionic conductance of the liquid and the electrolyte concentration in the liquid. So, kappa is very sensitive to how conductive the liquid is, or basically the concentration of ions in solution, and z0 is again the distance of separation. Between the two objects, whether it is a particle on a surface or two adjacent particles. Now, just like with the electronic double layer force, the ionic double layer force, which by the way this again is an expression for a sphere, in this case in contact with a smooth surface. You can see that again there is a linear dependence of this force on particle size. In fact, if you review, most of the forces that we have talked about, adhesion forces, have a linear dependence on size, which is why if you recall the equation that I wrote down first, the empirical equation based on experimental measurements, there is a linear dependence of measured adhesion force on particle size. So, in general it is true that most attractive forces or most adhesive forces tend to scale linearly with particle size. Larger the particle, the higher will be the force of adhesion. So, this ionic double layer force can again be quite significant, particularly when significant amounts of zeta potential are built up in solution. However, even in cases where you essentially have a neutral solution, there are still two kinds of forces that are set up in liquids which have a huge bearing on particle to surface adhesion forces as well as particle to particle adhesion forces. So, we will talk about those next. The first type of force is a surface tension force. Now, surface tension forces are important whenever you have two particles in contact or a particle and a surface in contact where there is an intervening liquid layer. Now, the liquid layer could be there simply because of high humidity, and again if you recall that empirical equation, you will recall that there was a dependence on the relative humidity, which is also roughly linear. So, clearly humidity plays a huge role primarily through the surface tension phenomenon. Now, the other situation where this can happen is if you have a surface on which you have particles and you immerse this entire system inside a liquid and then pull it out and let the liquid dry on the surface. Or alternatively, if you have a suspension of particles, let us say in a solvent, and you evaporate the solvent, so that you essentially turn a system that was initially wet into a system that is now dry. In that situation also, surface tension forces play a significant role, and the reason for that is if you have a particle sitting on a surface, when there is no intervening liquid, the forces of adhesion are primarily the van der Waals forces of adhesion and electrostatic forces of adhesion, right. If you have a liquid that is present, then again if they are charged particles or if it is a conductive or if there are ions present in the liquid, then again you can get ionic double layer forces. But let us say that you have a liquid which is neutral, there are no free ions. Let us take water and you have just wetted this surface with water. What is going to happen to it? Water will essentially wick between the particle and the surface and form a bridge. Now, this process is known as capillary condensation. Also known as liquid bridging. It simply reflects the fact that the liquid will try to get into the interface between the particle and the surface. It will try to wet the interface, and as it does, it will provide a surface tension force. Now, surface tension forces are always attractive. Surface tension forces will try to draw the particle to the surface and make it stick there. However, in order for that to happen, the liquid has to be able to wet the interface between the particle and the surface. That requires that the liquid have low surface tension. If it has a high surface tension, it is really not going to be able to penetrate into the interface between the particle and the surface. And so, you need a wetting agent in order to get the liquid to fill the interface between the particle and the surface, and surfactants and detergents essentially play that role. The reason you add a surfactant to water to improve its cleaning or a detergent to water to improve its cleaning, there is two reasons. There could be a chemical reason. For example, detergents can chemically dissolve organic materials, for example, but the physical reason is when you add a surfactant to a liquid, it lowers its surface tension and makes it possible for the liquid to now get in between the particle and the surface. See, again, the reason why it is easier to remove particles from a surface when it is immersed in a liquid, as we saw yesterday, the first reason is van der Waals forces are reduced. The second reason, actually we did not talk about it earlier on, the contact potential forces that I talked about, or even the Coulombic forces, they all have this dielectric constant as one of the terms, right. the dielectric constant of water relative to air is 80 times. So, if you look at the equation for the forces, the dielectric constant appears in the denominator. So, the Coulombic forces, the image forces, they are all significantly weaker in the case where water or a liquid is the medium. There is an immediate reduction in the electrostatic contact potential forces also by a factor of about 80. So, when you take a particle surface combination and immerse it in a liquid, everything is reduced. I mean, the van der Waals forces are reduced, electrostatic forces are reduced. However, the forces that could potentially increase are surface tension forces and ionic double layer forces. But surface tension forces will really not set in until you actually take the surface out of water. If you keep it immersed, this will happen, but as long as you keep it wet, the particles are still loose on the surface. Now, if you take this and you dry it, either just allow it to dry over time, or you actually provide active heating to convert this liquid bridge into a solid bridge, then the adhesion forces increase exponentially. Again, from our everyday life, the example is if you take a plate which you haven't cleaned and you just let it sit and you try to clean it afterwards, it's going to be hard because adhesion forces develop over time. Now, if you take that dirty plate and immerse it in water, but don't complete the cleaning, take it out and again let it sit, actually it's going to be even more difficult because now the particles are going to be solidly bonded to the plate surface because of this solid bridging phenomenon. So, the key point is that whether you are washing dishes or whether you are washing semiconductor wafers, never let particles dry on the surface after they have been soaked in a liquid because of this phenomenon. Initially you will form a liquid bridge between the particle and the surface, and eventually it will turn into what is known as a solid bridge. A solid bridge actually acts like a physical entrapment. You have to physically break it off in order to get the particle released from the surface. So, if you want to avoid particle adhesion to surfaces, it is very important to make sure that you never allow a particle to dry on a surface after it has been immersed in a liquid. Now, the force of attraction, the surface tension force, is, I am sure you are familiar with the equations, essentially 2 pi dp gamma, where dp is the particle diameter and gamma is the surface tension of the liquid. Of course, in this equation there is an implicit assumption that the contact angle is virtually 0. Surface tension forces really only come into play when you have low contact angles. In other words, the surface must be capable of being wetted. So, if you have a surface and the liquid does this, then surface tension forces become possible, because now if you have a particles sitting here, you develop this capillary layer between them. On the other hand, if you have a surface and you have a liquid on it which has a high contact angle, something that tends to bead up like this, right. Now, the particle to surface adhesion force is definitely not going to be increased by the presence of the liquid. In fact, it could reduce the adhesion force. So, it is a very important consideration that surface tension forces only come into play when the combination of the surface, the particle and the liquid is such that the liquid can wet the interface between the particle and the surface. So, if you have, for example, a hydrophobic surface and you have water as the liquid, it is not going to do this, it is going to do this. And so, surface tension forces are not going to come into play as something that increases adhesion forces. On the other hand, if you have a hydrophilic surface and water on top of the hydrophilic surface, it will spread nicely on the surface, and then as the particle approaches, the capillary condensation will happen and you will get bridging between the particle and the surface. So, the general equation for the force of adhesion is cos of theta, where theta is the contact angle. So, as the contact angle approaches 90 versus a low contact angle in this case, this will approach 0. So, surface tension forces can play a huge role, but not always. You have to match the liquid to the particle and the surface. Now, what role does surfactant play? The surfactant essentially will reduce gamma. If you plot the surface tension of a liquid against for example volume percent of surfactant, what kind of behavior will you see? It will be a rapid drop,